Hello and welcome to the New York City um, Category Theory Seminar. Today is October 20th, 2021, and we are delighted to have Dan Shiebler. Dan, you spoke in December of last year. You spoke about manifold learning and overlapping clustering and different types of metric spaces, categories of metric spaces. Anyways, Dan is a PhD student in Oxford, and he's working. Are you still working for Twitter?
Yep.
Okay, good. Anyways, he's talking about. Well, he changed his title, but he's talking about your new title is much more. He's talking about conextensions and machine learning. That's a good title. Anyways, Dan, take it away.
Totally.
Okay.
All right. So I'll be talking about some of the applications of conextensions to machine learning, and especially for kind of the process of generalizing from a training data set to a testing data set, which is something that we do very commonly in machine learning, and sort of the flow of inference in this process of machine learning matches nicely to the flow of conextensions. And so I'm trying to kind of formalize this intuition. So to say up front, this work is sort of inspired by a number of conversations I've had over a while with Bruno Gavranovic, and then also with my advisors, Kay, Zar, and Jeremy. All right. So I'll just start with a quick background on conextensions. I'm sure most of you are pretty familiar with them. And I found that this work was, I've always sort of known the definitions of conextensions, but it can be difficult sometimes to really get an intuition unless you have a particular couple of particular examples that you like to work with. So that this gave me an opportunity to kind of dive in and develop some intuition around what's really going on here.
Dan, we don't know. I mean, don't assume we know anything.
I won't. I'm going to go through the.
It is the hard. I think it is the hardest topic in category theory, and obviously the most powerful. But no, go on.
Yeah, I mean, I think a lot of this stuff. It's always people have different types of expertise and different types of things that they've spent a lot of time thinking about. I didn't get a chance really to think about conextensions before I started this project, and so it was a good opportunity for me personally to learn more about them. So basically, the structure of a conextension is we have three categories: A, B, C, and two functors: a functor from A to B and a functor from A to C. And we would like to derive the best functor f from B to C. So this is sort of the general pattern of what conextension is looking like. So kind of intuitively, if we think of G as an inclusion of A into B, then we're sort of trying to build some kind of extension of this functor K from A to C to a functor that goes from B to C. So basically extending from A to B as the sort of domain of this functor. So we could sort of think of this extension as like interpolations or extrapolations of our functor K from A to all of B when we have G as the inclusion functor. And for basically all of the work that I'm doing here, we're going to be using the inclusion functor for G. A couple of very small exceptions, so that this should substantially simplify the kinds of math that comes out of this. So more formally, we have that the left and right conextensions are actually pairs of these functors B to C along with a natural transformation from K to the composition of these conextensions with G or from this composition to K. So this is what distinguishes the left and the right. So basically whether we're kind of talking about the best among all of the functors that have natural transformations to K or natural transformations from K. So a very concrete example that I think really helps to sometimes clear up some of the details here is simply interpolating monotonic functions. So let's say that k is a function from the integers to the reals. So this could be any function. And we want to extend k to a function from the reals to the reals. So basically we want to come up with some meaningful things for k to be equal to on the numbers that are the non-integer real numbers. So in this case, k and f are these monotonic functions. Z and r are just pre-orders, the integers, the reals. And the left and right conextensions end up being the composition of k with the floor and ceiling functions. So the rounding down and rounding up. And so this kind of gives a little bit of intuition here on what these are doing. We sort of have the largest among everything that's lower bounded and the smallest above everything that's upper bounded. There's another example here with unions and intersections with sets that's kind of very similar to the pattern here, but you can kind of get the sense that we're talking about a sort of max and min based interpolation strategy. Okay, so now I'm going to dive into an application here of how we can utilize conextensions for classification. So maybe just to start with, like, what is the classification use case, and what are we really trying to accomplish? So in machine learning terminology, we'll say we have some kind of training data set. So some sort of set of samples, which are each pairs of something like an image or a set of text or some sort of feature vector, and labels of true or false, or 0 or 1. And the 1 being true and 0 being false. And so our, in this case, we have the objective be to come up with a function that maps each of these samples, given a element of our training data set, produces a true false value that's in line with what we see on this data set. And usually we think of this training data set as being a subset of some much larger sets. And so the function that we develop on this training data set is something that we can then generalize to a larger set. So for instance, we might be trying to classify images of dogs and cats. Our training data set is a whole bunch of pictures, some of dogs, some of cats, and we have labels for each of them of whether or not they're dogs or cats. We take this training data set, we build a function that's as good as possible over this training data set at mapping these images of dogs and cats to the correct true false labels. And then we can apply this function over the full set of all dogs and cats and see how it does. So this is sort of the generalization procedure. It's kind of why I've called this conextensor generalization. We're sort of generalizing from a training data set to a larger set. Okay, so kind of back to categories and conextensions. So we can try to characterize this structure, this classification structure, in terms of this pattern of categories and functors that we can apply a conextension to. So let's say that I is a pre-order. So this is kind of our full, I is like our full set of all dog and cat images or whatever else we have that's where we want to classify. And there's some kind of ordering relationship among them. And we'll talk a little bit about what kinds of ordering relationships are most meaningful in a moment. And we have some subset I prime, which is our training data set, essentially, with this sort of subset of images or subset of data that we're going to build our function over. And we have some kind of mapping K that maps from I prime to true false or to 0, 1. And we would like to learn a monotonic function from I to 0, 1 that approximates K on I prime. So just in terms of what the categories are here exactly, I prime is just a discrete category. So it's just the samples that we want to learn over. And K, because I prime is a discrete category, K can be whatever it wants. It doesn't need to obey any sort of ordering relationship or respect any kind of composition. It could just map anything in I prime willy-nilly to zeros or ones, similar to what we might observe if we actually looked at natural data. Whereas I has I prime as a subset of it and has actual pre-order structure where there's some kind of relationship between the objects. And so if we try to take the conextension in this case from I to false, true, or to 0, 1, there's sort of two pieces that are in play here. One is our original training data set labels, so how K assigns labels to everything in I prime. And the other is whatever is the pre-order relationship that we've placed over I. So whatever is the kind of set of morphisms that we are assuming exists or choosing to apply over our data sets, that is or the kind of full testing set that we would like to perform inference over. So the derivation of a mapping from I to false true is something that we can do with the conextension. And so this is what it looks like when we just actually take the conextensions here. So basically we are, it's like sort of a very simple rule-based structure. And just to kind of, they can intuitively, oh, this should be I, I'm sorry. I miswrote this error. So basically the left and right conextension split I into 3 regions. So I is a pre-order, and it sort of partitions it into 3 regions. A region where both of them agree that all the points should be mapped to 0, a region where both agree that all points should be mapped to 1, and a region where the left conextension maps everything to 1, and the right conextension maps everything to 0. So we can kind of think of these as sort of setting thresholds. Both left and right set thresholds at different amounts of once we've sort of, for everything that's in our pre-order that's above this line, we are going to be mapping that to true, and everything that's below that line will be mapping it to false. And so the left and right conextensions have different policies about what the conservativeness that they'll apply to this rule set. The left conextension is really trying to minimize false negatives. So it's mapping lots of things to true, and the right conextension is trying to minimize false positives. So it's mapping lots of things to 0 or to false when it's not sure. So here's just a concrete example, which should make things a little bit more clear. So let's say I is R and I prime is 1, 2, 3, 4. So we just have a very simple structure here. And we have K, our base functor that we want to base our conextension off, having this sort of false, true structure. So it's not increasing or decreasing, it's not monotonic, it's just alternating. So in this case, we have that the left conextension is going to be pretty aggressive. It's going to map everything over 2 to true, and everything less than 2 to false. Whereas the right conextension will be more conservative. It will map everything above 3 to true and map everything else to false. So the right conextension is not trying to not have any false positives, and the left conextension is not trying to not have any false negatives. And there's a disagreement region between these two. Between 2 and 3, the left conextension and the right conextension disagree. And on the other end, yes.
I'm not sure I fully understand what is going on right now. Doesn't the conextension and K have to agree on I prime?
They don't, because it's just the requirement is that there's a natural transformation from K to the composition of the left conextension of the inclusion functor, or the vice versa for the right conextension. So it's more like the conextension needs to be a lower bound or an upper bound, or the best lower or best upper bound.
Okay.
So that's the same. So in the case of floors and seals, they're able to agree. But in this case, the tricky piece here is that because K is not necessarily monotonic, it might be the case that there is no functor that agrees with K on I prime, because F needs to be monotonic, because I actually has these morphisms that add additional structure. So this is like the kind of two pieces that mediate what the conextension will be like. What are the morphisms in I that are going to create restrictions on what F can be, as well as what are the what is K actually doing?
One second, don't change. The category 0, 1 is discrete. There's no maps between 0 and 1?
The category 0, 1 has a map between it. It is a preorder.
Oh, so it's from 0 to 1.
Yeah.
Okay. And I prime are just preorders. Preorders or partial preorders?
Yeah. I is a preorder. I prime is just a discrete category. Whose objects are a subset of the objects of I.
Oh, okay.
Yeah, so that's why K can kind of map all willy-nilly, because I prime doesn't have any structure. It's just the objects and identities. Whereas I is a preorder, and so it needs to kind of, F needs to sort of respect this preorder structure.
Okay. Is there a reason why you don't want I prime to be a sub preorder?
Yeah. So it's like, for instance, I prime is representing natural data, like data we actually observe in the wild, and so that data might have any kind of labels. It might be corrupted. There might be just the fact that whatever function we're going to learn here is going to be something that's going to have some structure, but the data that we're training over is more complex, and so there's some structure that we're not capturing. It's very common for there to not be the same amount of structure in the natural data as in whatever function we're going to learn. And so the idea here is what we learn from I needs to be robust to the kind of noise that might be present in I prime, and that's why the left and right conextensions can disagree over I prime. Because they're sort of have different strategies for dealing with that uncertainty, and for dealing with the area of points where things are pointing in a way that don't support having K itself be functorial.
Okay, thank you.
Hey, hello. I'm wondering if you could expand upon what you said about the natural transformation. And is it, would you say that the natural transformation encodes the error in the approximation?
You mean from the natural transformations, these natural transformations from K to the left conextension and from the right conextension to K?
Oh, okay. Okay, that helps. Yeah.
Yeah, I mean, I think I wouldn't say that these are encoding anything about the approximation. I think these are more just defining what the strategy needs to be. So in that the left conextension and right conextension have different restrictions with respect to their ability to be above K or below K. Since the left conextension needs to be above K, it needs to have no false negatives, whereas since the right conextension needs to be below K, it can't have any false positives. So it sort of dictates what the strategy is for dealing with this intermediate region. So this kind of comes to the question of like the looking at this and sort of thinking through the how would we actually utilize this in practice, and how would we kind of build something that is meaningful when we have this region where the left and right conextensions disagree. And this region can be quite large. We have a lot of data that has a lot of kind of edge cases and can be pretty noisy, like the situation of natural data. it can be the case that this region is quite substantial and the left conextension or right conextension disagree on a pretty substantial portion of the data. So one strategy that we can try to do is to transform our data before we actually derive the conextension and try to minimize the size of this disagreement region, to minimize the size of the region where the places the left and right conextension map our data to is itself minimized. So basically, we tried to structure here. I apologize for the switching between false true and 0, 1. I meant to have everything be false true, but I missed it on the previous slides. But so it's false true is 0, 1 are the same thing here. But basically, we have instead of just simply taking the conextension from I to false true, instead we first transform I to I star using some kind of intelligently chosen function, and then apply our conextension over our transformed data. And one thing that we could do is try to minimize what I'm sort of calling the ordering loss. So this is basically an approximation of the size of this disagreement region. That can be kind of, this is specifically for the case where I is Rn. And we're trying to minimize the size of this disagreement region directly. In this case, the ordering loss is only equal to 0 when we have the left and right conextensions equal to each other. It's a kind of nice non-negative function. It's aggressively non-differentiable, but that's not a huge deal because we can use subgradient descent to solve solve non-differentiable functions without too much of an issue. It's well behaved enough to support subgradient descent, which I'm not going to talk about because it's kind of irrelevant to everything else. The bottom line is just if we can minimize this function, we can minimize the size of the disagreement region, and it's relatively easy for us to minimize this function using subgradient descent in TensorFlow. So the objective here, it kind of just like a sample. So I have actual experiments. We actually implemented this in Python. It's pretty simple to show that we could do this. We could sort of take this function, minimize it, map everything according to these conextensions, and then see what our actual performance is on natural data. So I took the fashion mnist data sets, which is a pretty simple data set, a bunch of really small 28 by 28 images of clothing to minimize our ordering loss over the task of distinguishing shirts from t-shirt images. So this is about 1/10 of this data set. So it's around like 6,000 images telling the difference of shirts and t-shirts. And then we can actually compute the left and right conextensions according to this diagram over those samples and check what the performance is. What is our false positive and true positive rates that we get after we kind of take this data, transform it so that it's kind of mapped onto a pre-order so that taking the left and right conextensions along that behaves nicely, and then see how well that actually performs in terms of like what's the false positive rate and true positive rate on those images. And if we look at extra new images of shirts that we didn't train it on. So we see pretty, okay results. Not what I would call state of the art, but pretty good, everything considered. So the first thing to note is that as we would expect on our training data sets, left conextension has a kind of perfect true positive rates, and right conextension is perfect true negative rates. So this is sort of exactly based on the constraints that's of how these are defined. The fact that there needs to exist this natural transformation, or these two natural transformations, is why we get these perfect true positive and true negative rates on our training sets. So on the set of samples we actually fit the data on. And when we generalize this to a larger set, to the testing data set, images that we didn't try to fit the model on, this pattern somewhat holds up, where we still have better true positive rates for the left conextension, better true negative rates for the right conextension. So this is sort of an illustration of how we can utilize this kind of pretty simple conextension structure for actually doing classification on real data. So what I'll do now is talk about a totally different example of kind of utilizing the exact same structure, the same pattern of conextensions and the same pattern of manipulating data for a totally different kind of application in a different set of categories. And these things are very closely mirror each other. So this is kind of a big block of text. So just the definitions of these categories. So there's sort of two main categories that what we care about in the kind of world of functorial clustering. So the first is the category of metric spaces and non-expansive maps. So in this category, our objects are metric spaces, and our morphisms are just functions that don't expand the distance between any 2 points. So that's if we kind of have a metric space, we apply this function, the image of any 2 points has either a smaller distance or the same distance, no expansion. And our category of partitions is a category where all the objects are a set and a partition of that set. And our morphisms are functions that are essentially refinement preserving. So if 2 points are together in our source partition, then their images are together in our target partition. So if we kind of have these two structures are sort of very similar to each other in that when we have points that are together or close together in metric spaces, and our morphisms preserve this togetherness, this is sort of mirrored in parts in that if 2 points are in the same partition in our domain, then they're in the same partition in the image as well. And so a clustering functor is just a functor from a subcategory of the category of metric spaces to parts itself. That's the identity of the underlying set. So basically what that's just saying is it's like a map from a metric space to a partition of that set that respects the distances. So if 2 points are close together in the metric space, then they'll be they'd be more likely to be put into the same partition as parts in kind of a nice way that obeys composition and has a nice structure. So there's there's a bunch of interesting research on this stuff, of kind of digging into what are the implications of these structures and how can you derive clustering functors in different sets of conditions. It's all very cool. I've looked into it a good deal myself, and there's a lot of very, very cool research that has sort of inspired everything.
And you spoke about it last year in the videos online.
Indeed, I did.
A plug for the New York City Category Theory Seminar.
Yep. Yep. Anyway, I love this stuff. I think it's Jared Culbertson and Gunnar Carlson both are kind of two people who've done a ton of work on this stuff that I've used as inspiration. Cool. So the objective of supervised clustering is basically if we have a clustering functor over some category of metric spaces, we want to find the best clustering functor over another category of metric spaces that that might be more restrictive or have a sort of different amount of structure in it. So here we have kind of a diagram here. So let's say we have, so T is some subcategory of Met. It's a subcategory of B, and then D is a subcategory of Met. And so we have some clustering functor K, and we have an inclusion from T into D. And what we want to do is want to take our clustering functor over our training set, our sort of smaller category or smaller metric space subcategory, and derive a clustering functor over our larger metric space category. So the interesting thing here is that D might have more objects, in which case what we're trying to do with this conextension is come up with a meaningful way to start clustering those objects, or it might have more morphisms, in which case we might be mapping things quite differently. We might, rather than try to, so similar to the previous case, rather than try to just expand the same strategy for clustering, we need to adapt the strategy for clustering in a way that obeys the new set of constraints. So this role, so there's kind of two additional potential areas for how D might be larger. This is the same pattern we have with I prime and I. So I, our preorder, has all these additional morphisms that I prime doesn't have, and it also has a bunch of additional objects that I prime doesn't have. And so F needs to both obey the structure in these additional morphisms, the structure in this preorder structure, in addition meaningful over all of these objects that aren't in I prime. And it's the same pattern here, except rather than just kind of elements of a preorder and preorder relationships, we're looking at metric spaces and non-expansive maps between them as sort of our source of structure. And so we can sort of think once again of K as our set of labels, essentially, so sort of a clustering of each of the different each of the different metric spaces in T, and F as our sort of function that we're trying to learn, our new clustering functor that maps metric spaces to clusterings. So in terms of how the conextensors are actually defined, essentially the two, again, are kind of the opposite ends of the spectrum. We could sort of think of the left conextension as coming up with the finest, most clusters extension of K, whereas the right conextension is sort of the coarsest, fewest clusters extension of K. So the left conextension is basically saying, if it's possible for these 2 points to be in different clusters, then put them in different clusters. Whereas the right conextension is basically saying, if it's possible for these 2 points to be in the same cluster, then put them in the same cluster. And you can sort of think about, like, if for a particular metric space in D, and we're trying to figure out, like, where do we want to map this metric space? How do we want to cluster this? This constraints on how this gets clustered is encoded in the set of morphisms that go into D and the set of morphisms that go out of D. The set of morphisms that go into D sort of mediate which points need to be put together, and the set of morphisms that go out of D sort of mediate the set of points that need to be pushed apart. And so that then this kind of like inward and outward sets of morphisms have a implication on what the which points can be need to be put together, which points need to be pushed apart. So there's some like subset of points that's both Lon and Ron are gonna have to agree based on like same cluster, different cluster, based on the sets of morphisms. But there's a whole bunch of other points that are not constrained. And Lon is gonna come up with a coherent clustering that's going to be pushing all those points into as many different clusters as possible. And Ron is going to be coming up with a clustering that groups all those points together as much as possible. And so these are kind of two reasonably coherent strategies to build the clustering for an arbitrary metric space based on the clusterings of a whole bunch of other metric spaces and morphisms between them that we're defining. So here is another little toy example now on what these can look like. So let's say we have T and D being these sort of simple categories where we have our, I said they're discrete. I'm sorry, that's a mistake. I meant as in there are morphisms between them, but the morphisms are the identity maps from x1 to x1, x2 to x2, etc. That's an error. But essentially, the mapping here is K will map x1 and x2 together, but x1, x3, x2, x3 will be mapped apart. So ln, because ln tries to create as many clusters as possible, and there's nothing forcing x2 and x3 or x1 and x3 to be in the same cluster, it will map x1, x2 into a different cluster from x3. However, because x1, x2 are forced to be together by K, ln will keep them together. So the only restriction on ln is that those two are together, and otherwise it will be able to push everything else apart. Ron, on the other hand, is trying to push as many things together as possible. And since there's no restriction that's preventing it from pushing everything together, it will do that. There's no there's no set in T that is x1, x2, x3, where x1 and x3 are different in different clusters, for example. Everything is just two sets, so there's nothing stopping Ron from just pushing everything into the same set. So this is sort of the structure here. We have the morphisms mediating what is possible, then ln and Ron taking the most conservative and most liberal perspectives on how to map things based on that set of structure that they both must obey. Okay, so I have another example of again with fashion mnist, because it's a great data set and a lot of fun, kind of trying to categorize how can we actually visualize what kinds of clusterings we can form here. So this example is a little bit more involved. So we have basically a training set of images in which like to cluster. So,
Dan, just say that sentence again, because your voice was off for a second. The training set.
Yes, a training set of images that we would already have categories for, or already are pre-clustered, and a testing set of images that we would like to cluster. So just in terms of what that looks like, we have this fashion mnist data sets where there's already labels assigned to these images. So we have all these t-shirts and pants and shirts and dresses and all these different categories of clothing, 10 categories of clothing. And this categorization that's already been defined on these clothing images already forms our training data set. It's sort of, this is our pre-clustered metric space or pre-clustered set. So we still need to actually define a metric over it. I'll just describe it in a second. But we can start by sort of thinking about this. This is a set, and we already have a partition of that set. That partition is the categories that the images fall into, or the classes they fall into, to avoid confusion. And we can construct a metric space from this with manifold learning, which I talked about a year ago. But basically we can kind of utilize a whole bunch of different strategies to take images and define metrics over them based on and any number of different types of strategies. We can put them all into a really big matrix, factorize the matrix, and then utilize distances between the factorized vectors, and a lot of fancier nonlinear techniques. Sort of identifying ways that we can use the pixel values that describe these images to then come up with some sort of distances between them that describe something a little bit more meaningful than just like what their pixel vectors would be. So UMAP is a very popular technique for doing this. It works pretty well for a lot of types of data. It works very well for small images. So that was what I used, is to UMAP to just sort of take these, take this fashion mnist and then map it onto a metric space for the training data set, and a metric space for the testing data set. So now we have, our training data set metric space, which is, this is just a category with a single object. That object is just our metric space for our training data sets. And K is our sort of a mapping of this training data sets to a single partition of that training data set, of like what is the partitioning of this into like the 10 classes that fashion mnist applies. Now we have another category which has two objects. So sort of our like I prime and I here are simpler in that I prime is just a single object category and I is just a two object category. And that category has the same metric space, and then also a testing data metric space, the metric space that we want to apply our clustering to. We want to cluster this second metric space in a way that is similar to how we clustered the first metric space. So this is sort of a very different take on supervised learning. We sort of have a clustering of one. We want to come up with a clustering of another based on morphisms between these two. And so morphisms between these two just need to be non-expansive maps of ways that we can map images in one to images in the other that respects non-expansive relationship. And then we can generate a partition of our testing data sets by taking the left and right conextensions, which will be based on two things. It'll be based on what are the morphisms that we choose to include between our training data set and testing data sets. It can be sort of any set of morphisms as long as this forms a category, as long as we have, you know, the kind of composition being respected and associative and all the other pieces. And that we have a respecting the structure that's in K, where K is mapping our training data set to a partitioning of it. And so what I did is I just generated a random category, basically. And I generated a bunch of random categories and tried to see what would the conextensions here look like? What would we actually learn? And so here's what we get. So here on the top left is an image of what the images in our fashion mnist look like once we use UMAP to project it down to 2 dimensions. And then we color them based on the category they fall into. So you see usually images in the same category tend to be close to each other. There's some exceptions, it's not perfect. There's some overlap, but there's a reasonably okay categorization of a location in images. And so we utilize this metric called the RAND score. The RAND score allows us to test how similar two clusterings are to each other. So we can compare our left and right conextensions to the ground truth with the RAND score. So that's what we get. We just generated a random category and looked at what our left and right conextensions actually look like. So unsurprisingly, the left conextension generates more clusters than the right conextension, as we would expect based on their definitions. And they both have reasonably good RAND scores with ground truth. So here I have, I just as a sort of comparison, I utilized the delta single linkage algorithm, where I chose the hyperparameter based on like a grid search to pick the parameter with the best RAND score. And the RAND score is comparable, but a little worse than this approach, which makes sense because this approach is actually trying to copy the ground truth clustering directly, whereas this is just utilizing sort of the best guess of what the clustering should be in unsupervised fashion. All right, there's other stuff here, but I figured I'd try to keep this short, take questions. Thank you, everybody.
Thank you. Thank you. It was perfect. I understood it. Any questions? Any questions? Any discussion? Anybody? Okay, I'm going to shut off the recorder. So maybe there's questions after the recording.